Welcome to this lecture on biostatistics and survival analysis. Today, we are diving into a fascinating and highly applicable topic known as bivariate normal dependent risk. Imagine a patient in a hospital whose heart and kidneys are both failing. How do we mathematically model the fact that these two vital organs affect each other? By the end of this video, you will understand exactly how to build a mathematical bridge between connected risks. To start, let us think about a delivery truck. If the engine overheats, it puts extra strain on the transmission, making it likely to fail too. These are not isolated events, they are deeply connected. In biostatistics, we call this a dependent risk. It happens when the presence of one disease or failure changes the likelihood of another occurring. For example, if a patient's heart begins to fail, their kidneys are placed under immense stress and may fail sooner. We cannot look at them as independent systems. Now that we understand what dependent risk is, how do we model it? The most powerful tool for linking two continuous variables is the bivariate normal dependent risk model. We assume the underlying times until failure for two different risks follow a joint normal distribution. We call these underlying times latent failure times. It is just a technical way of saying the hidden time an organ would fail if nothing else killed the patient first. The glue holding these two bell curves together is the correlation coefficient, which measures the strength and direction of their relationship. This brings us to the mathematical representation of our model. While this formula looks intimidating, it is just a recipe for drawing a three-dimensional mountain. It calculates the probability of both events happening at specific times simultaneously. The symbols μ1 and μ2 are the average failure times, while σ1 and σ2 measure how spread out the times are. The most critical symbol is ρ, the correlation coefficient. If ρ is 0, the risks are completely independent. If ρ is positive, the mountain stretches out diagonally into an elliptical shape. This joint formula we just saw leads us to an important question. What if we only care about one of the risks? Sometimes, even when two risks are connected, we only want to look at one while ignoring the other. This is called a marginal distribution. It simply means looking at the total probability of one variable by adding up all the possibilities of the other. Imagine taking our 3D mountain and shining a light from the side to cast a shadow on the wall. That shadow is the marginal distribution. Let us look at the mathematical form of that shadow. For a bivariate normal model, the beautiful result is that the marginal distribution of either variable is just a standard one-dimensional normal distribution. This formula tells us the probability of the first risk occurring at time x1, completely ignoring the second risk. Notice that the correlation ρ and the second variable's parameters are entirely gone. We can treat it as a simple bell curve. However, ignoring the second risk means we are throwing away valuable information that could help us make better predictions. To use that valuable information we were just throwing away, we look at conditional survival. Conditional means we are calculating the probability of one event happening given that we already know the exact outcome of the other event. In our medical example, if we know the exact time the heart failed, we can update our prediction for when the kidneys will fail. This gives us a new, updated expected time and a new, updated variance, which represents our uncertainty for the second risk. Here is how we calculate that updated prediction. This is the formula for the conditional mean of the second risk, read as the expected value of risk 2 given risk 1. It starts with the original average time for the second risk, μ2. Then it adds an adjustment based on how early or late the first risk occurred. This difference is scaled by the correlation ρ and the ratio of their spreads. If the first event happens very late and they are positively correlated, the expected time for the second event is pushed later as well. Before we move on, let us see this with a concrete example. Suppose we are studying heart failure, which is risk 1, and kidney failure, Risk 2. The average time to heart failure is 50 months and kidney failure is 60 months. They have a positive correlation of 0.5. A specific patient experiences heart failure at exactly 70 months. We want to find their new expected time for kidney failure. We start by writing down the conditional mean formula and substituting all our known values into it. Continuing with our calculation, we simplify the terms inside the parentheses. The ratio of the standard deviations is 1.2, and the difference between the patient's heart failure time and the average is 20 months. We multiply the correlation 0.5 by 1.2 and then by 20, giving us an adjustment of 12 months. Adding this to the original 60 gives a final answer of 72 months. Physically, because the heart survived 20 months longer than average, we now expect the kidneys to survive 12 months longer than the general average. Now that we have updated our expected time, what happens to our uncertainty? This is the formula for the conditional variance. Variance measures our uncertainty. The formula tells us that the new uncertainty is equal to the old uncertainty multiplied by a reduction factor of 1 minus rho squared. Because rho is a fraction between -1 and 1, squaring it gives a positive fraction. In plain English, knowing the exact time of the first event always reduces our uncertainty about the second event, as long as they are correlated. Let us apply this to the exact same patient from our previous example to see how much our uncertainty has decreased. Originally, the standard deviation for kidney failure was 12 months, so the original variance was 12 squared or 144. Now that we know the heart failed at exactly 70 months, we must calculate the new conditional variance. We start by writing down the conditional variance formula to see how the correlation of 0.5 reduces our uncertainty. Continuing with our variance calculation, we substitute the original variance of 144 and the correlation coefficient of 0.5. Squaring 0.5 gives 0.25. Subtracting this from 1 gives a reduction factor of 0.75. Finally, we multiply the original variance by this reduction factor. The new variance is 108. In plain English, by knowing the exact time of the heart failure, we have reduced our uncertainty about the kidney failure by 25%. The correlation acts as a bridge of information. To tie all these calculations together, let us look at this visually. The diagram you are seeing visualizes the joint distribution we have been discussing. The peak of the mountain shows the most likely combination of failure times. Notice the elliptical shadows on the floor? These are the contour lines. Because they are stretched diagonally rather than being perfect circles, they visually prove that the two risks are positively correlated. If you slice this mountain at a specific value of x1, the exposed cross-section is a smaller bell curve representing the conditional survival we just calculated. We have covered a lot of ground today, so let us summarize the key takeaways. First, dependent risks are deeply linked. You cannot study them in isolation. Second, the bivariate normal model allows us to link these latent failure times using a joint distribution and a correlation coefficient. Third, while marginal survival ignores one risk, conditional survival uses the known outcome of one event to update our predictions and shrink our uncertainty for the other. Understanding this is absolutely crucial for accurately evaluating medical treatments in the real world. Great job following along.